Have you ever wondered how the Earth was formed and how it might one day come to an end? The story of Earth begins within a massive spiral galaxy, the Milky Way. Around 100,000 light-years from its edge, a vast cloud of rotating dust and scorching gas drifted through the void. This simulation depicts a span of 50 million years, an instant in the endless timeline of the cosmos. During that era, millions of stars met their ends in violent explosions known as supernovae, shown here as flashes of light. These blasts scattered the fundamental materials that would one day form planets, elements such as carbon, silicon, and iron across the universe. The immense energy released by these supernovae caused nearby clouds of stardust to collapse. Dust and gas began to rush inward, pulled by gravity toward a dense core. This collapsing region was among the coldest places in the universe. Yet as more matter accumulated, the density increased and the temperature rose. Deep in this boundless interstellar expanse, a dramatic storm ignited at the core, a colossal and chaotic tempest composed of swirling dust, thin gas, and sparkling ice crystals. At the storm's center, temperatures surged. In this searing heat, a star quietly ignited. Our sun was born. The sun drew its energy from a slowly spinning disk surrounding it, the very cradle of our solar system. Within this mysterious and immense disk, the formation of planets began, a process both long and violent. In the beginning, tiny grains of dust gradually came together to form sand-like particles. Within the loosely packed clouds, these grains collided and merged, growing into pebble-sized bodies. Over the course of millions of years, through the slow passage of time, gravity gradually pulled these scattered objects together. They collided, merged, and eventually formed rocks, icy spheres, and massive boulders. These diverse objects, under the persistent tug of gravity, continued to cluster into small planetary bodies. Among the multitude of celestial objects, there was one unique body, Proto-Earth, steadily growing. Yet its fate at the time remained uncertain, shrouded in unpredictability and mystery. For a long time, we believed that the formation of planets followed a well-ordered and predictable pattern. Within our own solar system, the nearly circular orbits of neighboring planets seemed to confirm this idea. Not only that, but a clear distinction exists between the gas giants of the outer solar system and the rocky planets of the inner region. The gas giants include the massive and majestic Jupiter, the mysterious and elegant Saturn, the distant and icy Uranus, and the deep blue Neptune. Meanwhile, the rocky inner planets comprise the searing hot Mercury, the gentle Venus, our life-bearing Earth, and the resolute Mars. This clear separation began to emerge shortly after the sun ignited. The young sun emitted powerful solar winds, streams of intense heat that acted like an invisible barrier, pushing lighter elements such as hydrogen to the outer regions of the protoplanetary disk. The gas giants formed quickly in these outer zones, feeding on the abundant gases expelled by the sun and growing to colossal sizes. In contrast, the inner region of the disk, filled with dust but lacking in gas and ice, became the birthplace of rocky worlds like Earth. However, discoveries made by modern planetary telescopes have upended this neat picture. Astronomers have found gas planets roughly the size of Neptune frequently orbiting in the inner zones of other star systems, contradicting our long-standing notions of planet distribution. Even more astonishing, massive Jupiter-like giants have been observed orbiting extremely close to their stars, where the searing stellar winds are stripping away their atmospheres. In addition, scientists have identified a whole new class of planets, large rocky worlds known as super-Earths. How exactly did these distant planets manage to overcome immense obstacles and settle in such unexpected regions? And why have our own inner planets remained so clearly defined? These questions have puzzled astronomers for decades and remain some of the greatest mysteries in planetary science. In fact, much of what we know about the formation of the solar system comes from studying fragments of interstellar debris. However, most of these tiny particles are burned up in Earth's atmosphere as they fall, disappearing in bright flashes of light. Fortunately, some larger fragments survive their descent and reach the surface. Scientists study these precious remnants, planetary fragments, by analyzing variations in molecules known as isotopes. Through these detailed measurements, they have uncovered clues suggesting that these fragments originated from two distinct regions. the inner and outer solar system. This discovery points to the existence of a mysterious dividing force between the two regions, one that prevented material from freely mixing. If this immense boundary was caused by a young Jupiter, then Jupiter must have grown at an extraordinary pace. Acting as a cosmic wall, it could have blocked the flow of matter into the inner solar system, thereby preventing the formation of large rocky planets or so-called super-Earths near the Sun. Jupiter, throughout the vast and complex history of our solar system, has played a central and profoundly influential role. Its presence has shaped the very structure of planetary formation. Using the power of supercomputers, scientists have simulated Jupiter's formation by studying how dust, gas, ice, and massive rocks interacted over time. In these simulations, each brief flash represents a collision event, while every circular path tracks the orbit of a future planet. Under specific conditions, Jupiter slowly carved out its own distinctive orbit in the outer solar system, highlighted in blue within the model. As time passed, it continued to grow steadily, becoming the giant we know today. Soon after, Jupiter began spiraling inward along a curved path toward the Sun. Scientists refer to this dramatic shift in Jupiter's trajectory as the grand tack, a term borrowed from sailing, describing the moment a boat changes direction while heading into the wind. During this inward migration, Jupiter plowed through a vast cloud of cosmic debris. Much of the material it did not consume was flung outward, cast far beyond the edges of the solar system. As Jupiter continued its approach toward the Sun, simulation data indicates that it traveled as far in as the present-day orbit of Mars. This inward migration significantly depleted the mass available in the inner solar system. As a result, any planets that later formed in that region ended up being relatively small in size. Over time, another giant, Saturn, grew large and powerful enough to exert its own gravitational pull. Eventually, Saturn's influence reversed Jupiter's course, pulling it back outward into a new, stable orbit. At that point in the universe's history, Earth was still nothing more than a planetary embryo, just one of many celestial bodies in the process of evolution. With Jupiter retreating, Earth and dozens of other developing planetary bodies in the inner solar system were given the opportunity to freely compete for the remaining matter. Their survival and growth were left to the whims of cosmic chance. During the 50 million years following the inner solar system's formation, these young planets entered a chaotic phase, akin to a cosmic roller derby. Pulled and pushed by each other's gravitational forces, their orbits became increasingly unstable. Collisions became inevitable. In the end, after this intense period of planetary evolution, only a few possible worlds remained. Among them, the planets we recognize today. But there was at least one more world, whose existence was confirmed only after a landmark moment in human exploration. Following a series of scientific deductions, this planet's reality was uncovered after one of the most iconic events in space history, the launch of Apollo 11 on July 16, 1969. America's Saturn V, a heavy-lift rocket, would go on to successfully complete 13 missions in total, and each of those missions safely delivered its payload to the designated destination. The Apollo spacecraft landed on the Moon 6 times, setting down on its rugged, cratered surface. 12 astronauts stepped out of the lunar module, and during their close-up encounters with the Moon's environment, conducted a range of scientific activities. They performed various experiments, carried out precise measurements, and during their treks, on foot or by lunar rover, collected rock samples from the Moon's surface. When the astronauts returned to Earth, the entire world erupted in celebration. They were the first, and to this day, the only humans to leave Earth and successfully land on another world. At the time, few could have predicted that the rock samples they brought back from the Moon would lead to a cascade of groundbreaking scientific discoveries about both the Moon and Earth. Back in NASA's laboratories, scientists carried out extensive analyses of these samples. What they found was remarkable. Moon rocks shared many similarities with Earth rocks. Most notably, both had the same form of oxygen isotopes. This detail was viewed as a unique identifier for celestial bodies in the solar system, like a cosmic blood type. The Moon's surface, covered with massive and ancient craters surrounded by concentric rings, tells its own story. In recent images captured by NASA's Lunar Reconnaissance Orbiter over the Mare Orientale region, these geological features can be seen clearly. The rings suggest that a colossal object once slammed into the moon's molten, churning surface, creating shock waves that rippled outward like waves on water. Near the Apollo landing sites, astronauts discovered scattered deposits of relatively light rocks. These rocks were likely exposed when heavier material sank into the molten interior, pushing lighter matter upward. They also discovered a special category of rock, later nicknamed creep rocks. These samples contained potassium, rare earth elements, and phosphorus, characteristics of a type of rock known as anorthosite. These anorthosites are believed to be products of the moon's molten surface. But why did the moon have a global ocean of lava? And what exactly is the connection between the moon and Earth? The most widely accepted theory takes us back roughly 4.5 billion years. At that time, Earth may have been volcanically active, cloaked in a thin, toxic atmosphere. It was in the late stages of planetary formation, standing on the threshold of a monumental phase, the emergence and evolution of life. Far away in the vastness of space, a planetary body was slowly drawing near. It was a world roughly half the size of Earth. This celestial object was known as Theia, a unique planet that, in another version of the universe's evolution, might have coexisted with Earth as a separate world. But fate in the cosmos had other plans. When Theia collided violently with Earth, its journey came to a sudden and dramatic end. One can only imagine the overwhelming spectacle as this massive threat appeared in the skies, an awe-inspiring and terrifying vision from Earth's surface. The impact was nothing short of catastrophic. Theia struck Earth with the force of a cosmic storm, shaking Earth's very core. The collision was so intense that it tore away about 1/3 of Earth's outer layer. And yet, astonishingly, Earth was not destroyed. Instead, Theia merged with it, becoming an inseparable part of the planet. Thanks to advanced computer simulations, scientists have been able to reconstruct the breathtaking events that occurred in the first 24 hours after the collision. The immense amount of debris generated by the impact enveloped Earth, forming a thick atmosphere composed of vaporized rock. Over time, this debris cloud began to condense into a molten, glowing ring encircling the planet, marking the beginning of the moon's formation. This was the age of molten fragmentation. Most of the material orbiting Earth eventually rained back down in a barrage of fiery debris, like an endless storm of cosmic hailstones striking the young Earth's surface. But what's truly astonishing is that in just a single century, the remaining debris miraculously coalesced into a magnificent and awe-inspiring celestial body, our moon, Earth's faithful companion. After the impact with Theia, Earth entered a phase of rapid rotation. Its axial tilt shifted slightly compared to what it had been before. At that time, the moon's orbit was much closer to Earth than it is today. As a result, its vast, bright surface dominated the sky, looming large and brilliant overhead. As gravitational forces gradually pulled the moon into a more distant orbit, it began to exert a braking effect on Earth. This gravitational drag slowed Earth's rotation and helped stabilize the tilt of its axis. The moon, then, is not merely a cold and lifeless satellite. It is a silent witness and custodian of the cataclysm that nearly destroyed our planet in its infancy. From that distant past to our present day, the moon has become a constant source of comfort and wonder in our lives. It symbolizes a steady, dependable force, bringing serenity, harmony, and an eternal rhythm to Earth. Its unique glow, cast gently upon the surface of our world, paints an unmatched masterpiece of celestial beauty. Yet, it must be said that violence in the cosmos did not end with the moon's birth. Unlike Earth, the moon's special geological makeup and lack of atmosphere have preserved the marks of ancient events with remarkable clarity. It has not been smoothed over by erosion or hidden by plate tectonics. The scars of its past remain visible, a time-worn record etched into stone. In this way, the moon serves as a faithful chronicle of countless impacts that followed, a kind of ancient book that vividly tells the dramatic story of the solar system's early days, nearly 4 billion years ago. It speaks of a mysterious and turbulent epoch when Jupiter and Saturn experienced immense shifts, driven by the complex gravitational dynamics of the young solar system. A vast number of celestial bodies were hurled inward toward the heart of the solar system, like cosmic cannonballs, slamming into planets, moons, and other orbiting objects. To better understand this chaotic period, scientists conducted a landmark study. By analyzing the number and size of craters on the moon and using sophisticated computational models, they were able to simulate the intensity of impacts Earth endured during that time. The results were staggering. During this violent epoch, Earth experienced at least 4 massive impact events, each powerful enough to reshape the planet's surface and alter the course of its evolutionary history. These colossal projectiles struck with overwhelming force, crashing into Earth's crust, which was rich in radioactive elements like uranium and potassium. The tremendous energy from the impacts tore these materials from the Earth and flung them into the vastness of space. In the field of geology, this spectacular and complex process is known as impact erosion. The immense heat generated by the collisions formed a blistering outer shell on Earth's surface. As the intensity of these bombardments gradually diminished, this outer layer cooled rapidly due to its ability to dissipate heat. Meanwhile, in the quieter intervals between major impacts, smaller but more frequent collisions continued. These minor impacts delivered large quantities of water vapor into the freshly formed craters. In some cases, the shock of the collisions helped release water that was chemically bonded to minerals deep within the Earth's crust. Over the span of hundreds of millions of years, this sequence of events transformed the Earth. In the 500 million years following the Moon's formation, Earth gradually evolved into a world of water. Vast, endless oceans stretched across the horizon like shimmering blue silk, covering nearly the entire planet. Only a handful of defiant volcanic islands occasionally rose from the depths, dotting the watery expanse like scattered embers in a boundless sea. Like solitary sentinels of land rising from the sea, those early volcanic islands stood watch in a vast oceanic world. Meanwhile, the Moon remained in close orbit around Earth, its gravitational pull generating powerful tidal forces that shaped the planet's rocks, volcanoes, and coastlines. Earth's atmosphere was a mixture of hydrogen, nitrogen, and carbon dioxide, with water vapor suspended throughout. Both the land and oceans were rich in elements such as carbon, nitrogen, oxygen, and iron, all fundamental building blocks forged during the birth of the solar system. Earth had now assembled all the essential conditions for its most extraordinary achievement, the emergence of life. Yet, there was a looming problem. Earth's water resources were steadily diminishing. The young sun, though not as bright as it is today, was far more volatile, frequently emitting powerful solar flares. These flares struck the upper layers of Earth's atmosphere with immense energy. When charged solar particles collided with water molecules, they split them apart. Lighter hydrogen atoms drifted off into space, while the heavier oxygen atoms sank toward Earth's surface, binding with rocks. We now understand how devastating this process can be. Observations from spacecraft have revealed that Mars, in its distant past, once possessed abundant water. Its surface is etched with winding paths of ancient rivers and scattered with sediment deposits from long-lost lakes and ocean beds. Today, however, Mars is a lifeless world, with a thin atmosphere composed mostly of carbon dioxide. Instruments aboard orbital spacecraft have recorded the steady loss of Martian water, driven by relentless solar radiation. Scientists have also observed a similar process occurring on Earth's sister planet, Venus. The current atmosphere of Venus is filled with toxic chemicals, including dense clouds of sulfur. Its thick atmosphere contains extremely high concentrations of carbon dioxide, a potent greenhouse gas that traps solar heat. As a result, Venus has become a blazing cauldron, with surface temperatures nearing 500 degrees Celsius, making it the hottest planet in the solar system. Active volcanoes scattered across the surface of Venus further worsened its already hostile environment, constantly spewing sulfur and carbon dioxide into the atmosphere. So how did Earth manage to avoid such a grim fate? One key difference lies in a protective barrier that both Venus and Mars lack: Earth's magnetic field. This magnetic field deflects the most intense waves of solar radiation before they can strike the planet. It is generated by the thermal exchange between Earth's molten core and its outer crust. But this is only the first layer of Earth's defenses. As early as 4 billion years ago, another layer of protection began to take shape on Earth's surface. According to long-standing theories, heat and chemical reactions gave rise to proteins and nucleic acids, the two essential molecular structures needed to form life. More recent research suggests that early Earth was covered with hot springs and volcanic landscapes that may have fostered life. And yet no one knows for certain how life began or where it first took root. What we do know is this: life did emerge, and with one transformative breakthrough, the ability to convert sunlight into energy, it began to spread across the planet. Photosynthesis, the process on which all plant life depends, first appeared more than 3 billion years ago in primitive bacteria. Today, scientists using some of the world's most powerful supercomputers are working to unravel the chemical secrets of photosynthesis. The process begins with capturing sunlight. Light passes through a transparent membrane and reaches the core of the bacterium, where a cluster of spherical pod-like structures resides. Each sphere is equipped with specialized sensors designed to collect solar energy. When photons strike these sensors, they excite the chlorophyll molecules arranged in rings. This energy is then passed along a chain of proteins. Electrons and protons are shuttled through a series of chemical reactions, transmitting energy, a process entirely powered by sunlight. At this point, the cell must convert the captured solar energy into usable motion. The energy stored in protons drives this movement. These protons flow into the cell's aqueous interior, surging toward towering molecular structures. As they enter, the electrical charge they carry causes protein structures to spin like a crankshaft. This rotational motion triggers a chain of chemical reactions that are vital to all life on Earth. Two molecules combine to form a third molecule called ATP, often represented as blue in scientific illustrations. ATP, or adenosine triphosphate, is the universal energy currency found in every living cell that has ever existed. Like a biological battery, ATP stores energy captured from the sun and repackages it into a stable form that cells can use to break down nutrients, power movement, support reproduction, and sustain essential life functions. The emergence of ATP allowed microorganisms to thrive and multiply. As bacteria evolved into early plants, photosynthesis entered a more advanced phase, one that began producing a byproduct, oxygen. The amount of free oxygen generated soon exceeded what the land and oceans could absorb. In the atmosphere, this oxygen bonded with hydrogen, preventing its escape into space and forming new water molecules in the process. This ongoing reaction gradually slowed the loss of Earth's oceanic water. But it could not stop it entirely. Recent studies have revealed that Earth may have already lost up to 25% of its original water reserves. On Earth's surface, water, life, sunlight, and geological activity work in unison, powering a remarkable planetary engine. Climate patterns are influenced by the planet's daily rotation, seasonal changes, and the uneven heating caused by the sun. These forces regulate global temperatures, driving warm equatorial winds toward the poles and sending cold polar air back toward the equator. Tides and ocean currents mix deep, cold waters with warm surface waters, helping to maintain thermal balance. On Venus, solar energy and carbon dioxide became destructive partners. Water vapor and greenhouse gases were trapped in the dense atmosphere, fueling an inferno. In contrast, Earth's climate is moderated by a critical factor unique to our planet: life itself. The oceans are filled with chalky plankton, tiny phytoplankton capable of absorbing carbon dioxide, whether it's churned in by ocean waves or drawn up from the deep by currents. These microscopic organisms carry carbon atoms up the food chain. Phytoplankton become food for zooplankton, such as radiolarians, creatures that have existed for over 500 million years. It was during this time that life was erupting across Earth's oceans in a tremendous burst of diversity. From a classification perspective, copepods, tiny arthropods similar to crustaceans, emerged as one of the most abundant sources of protein in the marine ecosystem. Even octopus larvae, members of this vast and intricate ecological web, were so small they were barely larger than the tip of a human finger. Zooplankton were consumed by small fish, which in turn were eaten by larger predators. At every stage of the food chain, carbon that once existed as diffuse gas in the atmosphere was passed along, moving from tiny organisms to larger and larger animals. Typically, the larger the creature, the greater its carbon mass. From enormous whales to microscopic phytoplankton, marine life forms are vital components of the planet's global ecosystem, one that can extract carbon dioxide from the atmosphere and gradually return it. The key to the carbon cycle lies in Earth's ability to store carbon over long periods. Today, scientists continue to monitor chlorophyll, an important chemical tracer used to study plant growth. As the seasons shift, plants absorb large quantities of carbon dioxide and release the oxygen we breathe. On land, when plants and animals die and decompose, the carbon they contain is transferred underground. Earth itself also plays an active role in this process. During rainfall, exposed rocks absorb atmospheric carbon dioxide. Through erosion, this absorbed carbon is eventually carried into the ocean. If carbon-rich material becomes part of the marine food chain, over time it may settle and transform into fossil fuels like oil, or into carbon-bearing rocks such as limestone. Once these sediments are exposed at the surface or affected by volcanic activity, the stored carbon is released back into the environment. Every year, volcanoes emit over 100 million tons of carbon dioxide into the oceans and the atmosphere. The carbon cycle plays a crucial role in shaping Earth into a habitable planet. Its effectiveness depends heavily on the presence of life. Today, Earth boasts vast oceans, a dynamic and ever-changing atmosphere, and solid continents. Sunlight bathes the surface, warming the planet and creating a world where life not only survives but flourishes. It is a place of abundance and ecological balance. As we continue to study Earth and unravel the mechanisms of this intricate system, we are continually amazed by the precise coordination and synergy required to sustain it. The remnants of ancient supernova explosions, Jupiter's powerful gravitational influence, a cosmic collision, and the birth of the Moon. Each of these events played a vital role in shaping Earth's water systems and ultimately led to the emergence of life. The more we are able to reconstruct the story of Earth's evolution, the more we are struck by its wonder and improbability. We are coming to realize that countless other star systems exist throughout the cosmos, and this raises a profound question. Is Earth merely one among many life-filled habitable worlds? Or is it a singularly unique product of extraordinary cosmic coincidence? Our planet resembles a paradise, but we are left to ponder, could it be the only paradise in the universe?